Okay, let's finish this example from yesterday. We want to find we want to find the derivative of this thing, right? So taking the derivative ddx of this function here in the blue box. And so we're going to write this as a composite function because our fundamental theorem of calculus says if I have an integral that goes to a variable bound from a fixed bound, I can call that a function. Right? This is an area that changes depending on what this value is. So this value is the input variable, and then the output is the area between A and that input variable. I take the derivative of that, I just get the function that was inside the integral. Okay, so we need to set it up that way. So we're going to define f of g as the integral of the cosine function. It's going to start at 0, it's going to end at g, just like this setup, right? So if I have that set up, what I can do here is I can put in f of the square root of x and think of this function here as a composite function of f and the square root function, right? And so the derivative of this composite function that uses the chain rule. And so it's f prime at the square root of x times the derivative of the square root of x, which is 1/2 x to the minus 1/2. So this is just the chain rule. Okay. F prime is just the cosine function. So this thing turns into the cosine of the square root of x times 1/2 x to the minus 1/2. So we're just going to use the chain rule on some of this type of stuff to do these problems. Let's do another one. Say I want to find ddx for the integral from x to x squared of, let's do e to the x dx. Okay, so I've got to rewrite this because right now I've got variables on both ends of the area. So I'm going to rewrite this so that I have a fixed endpoint on the areas. So we're going to rewrite this using some of our rules as ddx. This is going to be the integral from 0 to x squared, e to the x dx, minus the integral from 0 to x, e to the x dx. Okay, so picture-wise, x squared. If I want this area, so what we're doing is we're taking the purple area and then we're going to subtract the yellow area and we get the area between x and x. Okay. Now, why did I do that? Is because I wanted a constant bound on the bottom end so that we could use the fundamental theorem of calculus. The fundamental theorem of calculus says if I've got a constant bound down here, my variable's up here, then the derivative of this function is just the inside function. Okay. So this bit is set up immediately for the fundamental theorem of calculus because I've got just a single x up here. This one isn't just an x, it's an x squared, so I'm going to have to use the chain rule again. Okay, so the chain rule on this is going to be e to the x squared, because the derivative of e to the x is just e to the x. We put in the x squared, multiply by the 2x, and then minus e to the x. Where do we have questions on these? See if I can find another one. Here's another book one. Why don't you guys take like 2 minutes and see if you can do this one. Okay. So the derivative of the integral is just the inside function, but it's going to be applied to the variable bound up here. And then I have to multiply by the derivative of the variable bound. So this all turns into 4t to the 5th. Right? Where do we have questions? Okay, what questions do you guys have over homework? That's kind of the end of 5.4 stuff. What's homework questions you guys have? We're all good on 5.3 stuff, 5.4 stuff? We haven't probably started yet. 11. X squared minus 64. X minus 16. Oh, for the next one. Okay. So I need to find an antiderivative for this. And when you're dealing with exponentials, you get the same exponential back usually as part of it. So we're probably going to think that the antiderivative for e to the 3x times 3, it's probably going to look like some constant times e to the 3x, right? Okay. So I'm just going to differentiate this and see what that constant would have to be. So if I take the derivative of this, I'm going to get the constant times e to the 3x times the chain rule would tell me 3. And I want it to be exactly that, so I'm just going to make the constant 1. So this is my antiderivative. Okay. And then the fundamental theorem of calculus says if I want to take this definite integral, I find any antiderivative. This is one of them. Sorry. This is the antiderivative with just a 1 here. So that's my antiderivative. I find any antiderivative, and then I evaluate at the top limit and the bottom limit. So this integral from 0 to natural log of 5, 3 to the 3x dx is going to be e to the 3x evaluated at 0 and natural log of 5, which is e to the 3 natural log of 5 minus e to the 0, 3 times 0, which is 0. So this is e to the natural log of 5 cubed minus e to the 0, which is 5 cubed minus 1, which is 124. Where do we have questions on that? Sure. This one? Okay, so we want the derivative of this. So this is like what we were just doing. So we're going to take the cosine, put it in an integral. The upper bound is the sine inverse function, t dt, and we want to take a derivative of this. Okay, so this, it's going to be the cosine function, the inside function of the integral, applied at the upper bound. And then I have to multiply by the derivative of that sine inverse function. Does anybody remember what the derivative of the sine inverse is? Yep. We're good with this? Hard part's probably remembering that bit. Okay. What is the cosine of the sine inverse in terms of x? Sine inverse is an angle, so we're going to put that down here. That's sine inverse of x. If it's the sine inverse, that means that the opposite over the hypotenuse is x. And then on this side, I get the square root of 1 minus x squared. So the cosine is square root of 1 minus x squared over 1. Okay. So if I plug that in, I get 1. What do we know about functions that have a constant derivative or a derivative of 1? They're linear, right? Okay, so this is equal to x plus some constant c, because the slope of this function is 1. So if I would get rid of the integral, it's just going to be the integral of that thing's a linear thing. It's x plus c. For this is just going to be 1. If you stop here, it doesn't look like 1, does it? Other questions we have? Right. So the test will be, I think I've got it set up for Wednesday after Thanksgiving, I think. You have all Thanksgiving to review. So let's see. So today is Wednesday and 5.3 is due. And then Thursday, Monday 5.4 is due. No, Friday 5.4 is due. Monday of Thanksgiving week, 5.5 is due. 5.6 is due. There is in the book, because they're not in the. Yeah. So 5.6 due on the 30th, which is right after you get back from Thanksgiving. And then we'll have, a day there, and then Wednesday will be the exam. So there might be 1 or 2 questions on the final, one from each of the sections, but not a separate test on the chapter 6 stuff. Yeah. That seemed to work, at least relatively okay. So you'll have 2 hours for it. So I'd say 25 to 30. Well, it'll be during finals week. Yeah. I'm gonna try and put up the project this week. Still. I've been telling you that for a while, but been trying to figure out what exactly I want to do with that. So either this afternoon or tomorrow, probably I'll have that final up, or the project up for you. What are you guys' thoughts on after Thanksgiving? Do you guys want to come back to the classroom? Or I know a lot of people are just going straight remote after Thanksgiving. Is that true for some of your other classes? Some? To stay in person? So you'll be around no matter what? To be your only in-person class? Either way. Sure. Yeah. No. I mean, kind of like what we're doing now. Yeah, I'm okay with doing what we're doing now. That's fine. Yeah. Yeah, I think so. I thought I changed them on my lab math. I haven't put anything in Canvas yet, but I think I updated all the scores in my lab math at least. Okay, we'll just kind of continue things as they are then. So if you wanna stay remote, Zoom in, we'll keep doing that. Other questions for how the semester is going to kind of wrap up? Yeah. So in the past, when I've had in-person stuff, I've given stuff in 2 parts, and you do part 1 on one day and part 2 on the other day. With the online stuff, I mean, that still could make sense. You guys want a 2-part final? In the past, I've given a 2-part final on these 5-hour classes, because these 5-hour classes give us 2 periods for finals. And so I'll give something over chapters 2 and 3, and then something over chapters 4 and 5, or something over chapter 4 and 5 and 2 and 3. Does that make sense? Or sorry, 2 and 5 and 4 and 3. So you kind of split up a hard chapter with an easy chapter sort of deal. Does that sound okay to you guys? So I just have never given online type finals before, and my finals, they're usually around 10 questions on each of the days. And so, and then the style of how they are, they're hard tests, and you're only supposed to get like, well, you're supposed to get as many points as you get, but I write them out of like 150 points, and I expect you to get about 75 points because they're hard tests. And so I can't really do that with this. So I haven't really thought about that. I would assume if we do 2 parts, it'll be about 20 questions on each day. So slightly more questions if we do the 2 parts. Yeah. Two hours each day. Because you get the full finals period for 2 different. So basically we treat this as a Monday, Wednesday, Friday 8 a.m. class and a Tuesday, Thursday 8 a.m. class. And you get the finals block for the Monday, Wednesday, Friday class and the finals block for the Tuesday, Thursday class. So we will be done with new stuff after the 6.2, which would be that Monday. So the test is on the 2nd, I believe, which is that Wednesday. 6.1 would be due that following Monday, because we usually have that day after the test off because I haven't given you new lecture stuff. So 6.1 will be that Monday. 6.2 will be due that Wednesday, but then we'll have basically all of that week to review because I will have gone over the 6.1 and 6.2 material starting Thursday and Friday of the previous week and probably finishing up Monday or Tuesday of that week. So we'll have a good 3 days for review probably. Right. The math. I'm not going to critique spelling so much. I mean, if you're misspelling every other word, yeah, okay, I'm going to be a little upset. But I'm not going to grade on grammar or punctuation or citation correction, like how it's cited and that sort of thing. But what I do want to see is a good explanation of why you've done what you've done. I don't want you to say, okay, here's the equation 2 plus x equals 3 and say, I took 2, I added it to x and I got 3 in your sentence. That's just redundant because you already told me to take 2 plus x and get 3. What I want is why did you get that equation in the first place? How did you get this? What was your thought process about this thing? Does that make more sense? Okay, so I want to see detailed explanation of like how you were thinking about things and why that thought process is a valid thought process. It's justification of doing what you're doing. So yeah, sort of like a proof, but I'm not going to ask you to prove anything. Like, yeah. If you want to. Yeah. So if I like ask you to maximize something, you're like, you can cite, I don't know if there's a specific theorem that you would use for optimization type stuff, but you could cite like, we're going to use the first derivative test to make sure that this is a maximum or a minimum. And then you have to justify like how you use the first derivative test. Yeah. Yeah. Or like, we use the intermediate value theorem to prove that there's a root here. So there is some maximum in this area or something like that. So I will give you pretty much the thing that you want to solve. But I'm not going to specifically say, okay, this is the equation that you need to solve type deal. It's going to be more like a read this paragraph. It's going to be an extensive word problem is basically what it is. Yeah. So you have to kind of analyze the situation, decide which math is appropriate, apply that math, and explain why that was the appropriate math and why what you applied or how you applied it was the correct thing to do. 2 to 5 pages, probably. Yeah, a thorough explanation. 2 would be probably on the short side for some of this stuff. But. Other questions? Okay. So we've got this function here, which is it's a quadratic. It's just your basic parabola x squared, but it's been shifted to the right by 4. So this is the basic parabola shifted to the right by 4. So we picked that one. And then I think I probably still have the notes from yesterday here. Okay, so we have the right parabola, which was shifted to the right by 4 here. And I'm just going to shift it back because if I shift the whole thing back, what I was trying to do is I was trying to find this average value or what the rectangle would be so that like this area plus this area was equal to this area so that it kind of leveled everything out, made a rectangle. Well, it doesn't matter that it's between 0 and 9 because I shifted it. So I'm going to shift it back to be between -4 and 5 by shifting it back left. And then I just have to deal with the original equation of x squared, t squared, that parabola, instead of the t minus 4 squared parabola. It just makes the algebra easier. So what I'm going to do is I'm going to take this integral for the average value instead. And you can take this integral because I'm integrating the area under the t squared function from -4 to 5 over a width of length 9. So the 1/9 is the width of length 9. This is the area, total area under the curve. So divide the total area by the width and you'll get the average height. Does that make sense? You don't have to. It works out fine the other way too. So if I want to integrate, I can still do 1/9 integral from 0 to 9 t minus 4 squared dt. But what I'm going to have to do is I have to expand that out. So you got 1/9 integral 0 to 9 t squared minus 8t. Plus 16 dt. So if I find an antiderivative for this, which we didn't have at that point in time, but we have now, so we'll do it with the antiderivatives now. So I've got an antiderivative for this is going to be t cubed over 3 minus 8t squared over 2 plus 16t. That'd be my antiderivative for those things. And I'd evaluate it at t equals 0 and t equals 9. So I get 1/9 of putting stuff 0 in here, it's all going to be 0. So I'm going to have a big -0 at the end. But putting 9 in here, I get 9 cubed, which is 729 729 over 3 is 243 minus 4 times t squared. T squared is 81. 4 times that is 3. 24. And then plus 9 times 16, which would be 144. And so you're still going to end up with 287, 1 over 9, 387 from the 144 and the 243 minus 324 equals 1 over 9 times 63, which is equal to 7 still, which is what we had here. I just thought that was the harder way than to use the geometry and shift it back. Okay. Other questions we have? Anybody online have stuff to talk about? Okay. Come with questions tomorrow. Otherwise, I'm going to start moving on to 5.5, 5.6 stuff. We're going to start using substitution things because that's 5.5 and 5.6 is substitution integration technique. So we'll get our first integration technique, which allows us to find antiderivatives for things that aren't just simple functions that we've seen before. And so we'll do that. Integration is harder than differentiation. You can't always integrate stuff. You can pretty much always, if you can write it down, you can differentiate it. If you can write it down, you may or may not be able to integrate it. Integration's hard. And so there's a lot of techniques out there that are very helpful, but there's no like definitive way to do stuff. With differentiation, if you have your chain rule, your product rule, your quotient rule, you have your rules, you can basically differentiate anything you would come across. But the integration, that's tougher. Anti-differentiation is tougher. Okay. I will see you guys tomorrow.